أعوذ بالله من الشيطان الرجيم بسم الله الرحمن الرحيم السلام عليكم ورحمة الله وبركاته. Good morning. Salam jatuh to everyone. Will anyone respond that whether you received my voice or not? Thank you very much, Ko. Shukran Billah, can meet again today on the 26th of December 2021, or in Islamic calendar is 2021 or the 21st Jamadil Awal 1443. Our class is a 2 hours class from 8 a.m. to 10 a.m. And we are going to talk about the vibration, typically focusing on free undammed vibration. So thank you again for joining the class. So I'm going to share with you the last. I'm going to stop here and I'm going to share with you this one. Pendulum, we completed this one. Yeah, before I try to or perhaps continue the lecture online as usual. I'm going to what do you call it? I'm going to give you highlight notes or perhaps a captured thing that we have studied or we are showing uh, knowledge about this one last week or last meetings. Yeah. So that you can basically follow and you can recall whatever we have discussed in class. Okay, first foremost, this is the last topic in your syllabus. We are talking about vibration here. This one is the vibration. This one is the vibration. You have the blank display or the blank screen with you, student, class. Thank you, Go. So we are talking about vibration. We have a couple of things here. One will be, right beginning is 1 degree of freedom. This one will be 2 degree of freedom. And the 1 degree of freedom or single degree of freedom, we will cover, inshallah, talking about this one, couple of things. This is free on them, today works. Vibration, of course, this one is the free, also free, but now it's them vibration. And last but not least will be force them vibration. So this one we will talking about all. This one is vibration, yeah. And we already covered a bit here on free and them. So the next part of meeting, perhaps a couple of weeks ahead, we are going to look for the 2 degree of freedom, and we don't know what is a degree of freedom. We already discussed, and we are going to cover, inshallah, the free also on them. This one also free. So sorry, this one force and them. And typically for the force here, we're going to to do a bit about absorber, or perhaps we call it as tune mass damper. This TMD is not turning moment diagram, but yet is a tune mass damper. Tune mass damper. Okay, so we already covered a part. It's not a part, only a small part of free undamped vibration. Free undamped vibration. And we have 3 different systems. We're going to focus. The first one is spring mass system. Spring mass. A lot of example in spring mass system. Then we're going to go for pendulum. And last but not least, a bit about shaft plus. And our aims here, our objective here, our aim here, our task here is to define the omega n. Okay, is to look at the omega n, or perhaps this is the major part of our work. So beside this one, if you can calculate the omega n, so we're going to proceed about Tn, perhaps Tn. This one is the natural frequency. This one is the periodics. Periodics. Or perhaps in other word, yeah, you know, you call it time. It's a vibration time oscillation in one cycle. Okay, so to calculate, perhaps if I may say here, to calculate the omega n, we're going to use couple of methods. One method is a classical one. Classical is a Newton's law, or second Newton's law. Yeah, Newton's law. The other one is the energy method. And last but not least, be the equivalent method, also known as Lamé system. Okay, so as we completed the spring mass system, what we did was last meeting, yeah, we have the spring mass system. It doesn't matter whether your system been suspended or supported. What we did was, this is suspended. This one is K is M, and finally we get the result of omega K by in radian per second, or in hertz we have omega n by, or 1 by 2 pi K by with the units of hertz, huh? So uh, uh, in doing this calculation, remember you have I think I already mentioned, or perhaps I use, solving the omega n by, remember, number one, by what? Harmonic solution. In the harmonic solution, by saying that let x is equal to x sine omega t. You have x dot, or perhaps this one dx by dt with respect to time. You have this one is omega x cos omega t, and finally you have this 2x by dt square. You have the x double dot equal to negative omega square x sine omega t. Isn't it this one? Remember? Then substitutes in general equation. It's not general equation. It's not general equation. It's basically what? Equation of motion. The other, the other method, perhaps in calculating or in solving the omega n, is by equating the equation of motion, by equating the equation of motion of simple harmonic motion with, sorry, this one is not correct, huh? By equating the equation of motion of the system, with, this one is differential equation of motion of simple harmonic motion, or in other word, or in expression, I might put it here as x, this one here, x double dot plus omega n square x equal to 0, or you have y double dot plus omega into y equal to 0, or this one is for rectilinear motion. The other one, you have this one theta double dot plus omega n square theta equal to 0. This one is the angular motion. So these are the things they already covered in our first meeting. So inshallah, by refresh or perhaps by recapture thing that we already discussed in class, last meeting, basically you can really understand where we are, in solving the vibration problems. As for today, we are going to look for pendulum. Oh, before that, I already covered this one. Where are you? This one, yeah, classical method. Methods to calculate omega n. Methods to calculate omega n. One will be Newton's law. Second law, this one, as you have this one, you have to use equation like F equal to ma, or in other words, x double dot. Then you have the summation of moment or torque equal to I alpha, or perhaps in other words, I theta double dot. Then of course you need free body diagram. So number 2 here is the energy methods. Energy method. You have the energy method equation is d by dt. Remember, this one is PE plus KE equal to 0. Some book, if you read book, yeah, for example by Timson or Kinkel, they put it here as d by dt. It's not PE by K, but instead T U, where your T is the this one is basically cross this one. This one is basically cross this one. So this one in books, in many book, they put it as T by U, T plus U. And last but not least, the last method is the equivalent method, EQUI. Astaghfirullahaladzim. It's QUI, yeah? It's a QUIVALEN equivalent method, which cover, or sometime in book they put it Lames system. This one is, simplify the complex model to simple model by using the principle by applying conservation of energy, where your energy before must be equal to energy after. This is your principle. This is what we call as the principle. Okay. I haven't talked about this one yet because we haven't meet any any complex model at the moment. So I've been I already talked a lot of Newton's law and energy methods. So as for today, we're going to look for pendulum. So a simple pendulum, this one simple one, already covered. Last meeting was a simple one, already covered, is this one. This is, you give this one theta dot theta double dot, and we are saying that this one is m, of course, at the L from the O here, fixed point. So you have your summation of m about O equal to I about O theta double dot. And finally, when you are doing all the necessary free body diagram. For example, if I can share with you, or perhaps put it here, your free body diagram. This one is the mg. You have this one is the mg sine theta. You have another one component of mg cos theta. So for the moment here, because this one rotating that way, so your boundary condition will be rotating counterclockwise. This is your boundary condition, yeah. Okay, so what you have here is, okay, the negative mg sine theta, this one by L, correct? There is no any other forces, isn't it? So equal to this I naught theta double dot. And we can, expand this I naught. I will be the mass moment of inertia of mass M. So you can, this one, expand this one to become what? To become M, this one L square. This is coming from the equation of mk square that we found that k equal to L. So we already done that one, yeah. So with that, I think make your interest in vibration is more, yeah. This one is sine theta by L. Open up the bracket. Oh, sorry. Expand the equation, becoming ml square theta double dot. And but for small displacement where theta approaching to 0, you found that your sine 0 equal to 0 and your cos 0 equal to 1. So we are seeing here sine theta equal to theta. So you take this one and put it here. This one sine theta. So finally your equation becoming what? Your equation becoming mg. This one is theta. This one is L. Then we have I. We already change this I is ml square theta double dot. Correct? Then you simplify, you'll be getting theta double dot plus this one is equal to ml square. This one be divided by mg. This one is mgl, of course. Bracket theta equal to 0. Cancel, cancel. This one cancel and cancel. So your equation of motion now becoming theta double dot plus g by L, theta equal to 0. Correct? And this one I already mentioned about. You can solve this one by using two methods, isn't it? By using two methods. One will be solve this one, solve by using what? Harmonic equation. Or you can also solve by using equating with differential equation of motion of simple harmonic motion. We done this one in our last meeting. So we stop at here. We stop at. So as for today, we're going to look the same system now using energy method. Energy method. So the equation is d by dt. This one is PE. I keep the equation as PE and KE because you are very familiar with this term, yeah, PE and KE. If you read, if you go for, if you check on book, you have this one T plus U equal to 0. It's basically this one is same. Okay. So for the next thing now, what I intend to share with you is you have to look for energy because we are dealing with energy. So the KE is basically the what is the potential and sorry, it's the kinetic energy is the half mv square. But remember, this energy is basically is basically for linear. So you have to convert this one to become v equal to omega cos r. So you have here m, this one the omega square r square. Because the pendulum itself, you look at the pendulum here, this one is let's say this one L, yeah, this one is M, yeah. You found the mass moment in nature is basically ml square. You have here, if I can change the color here, you have M, and you have this one. So it, it shows that it can be representing the ml square. So you put it here as I about O, then is the omega square. So this one, your I now about O is equal to, this one is R, so you have m r square. Okay, so you have this one, okay, for kinetic energy. For potential elastic energy, what you have is, so you know that the potential elastic energy, if you can draw this one, yeah, if I can put it in another color so that you can differentiate the thing that we discussed here. So you have here, so you displace, so you will move at that point, so then you will be, you will, as you display, then you hold a bit, then you let it go, so it will be, and this is your parts, the pendulum part, isn't it? So the potential energy is basically what? Delta H. It's the difference in altitude, isn't it? So delta H, so you will have some, yeah, so this is your delta H. Correct? This one is L, this one also L. Am I correct or not? Yes or no? So your PE now, yes or no, class? Why everyone is so quiet? Okay, so your PE, what is your PE now? Your PE is basically, remember your PE? PE is given by mg delta H. So the delta H is the difference between the position when you displace and the initial position. This is the maximum. This one is the maximum position. Maximum position when at statics. This one's the maximum position when you give small theta. Correct. So maximum position at statics. So you found that this one is the mg delta H, isn't it? It's mg delta. This one is delta H, and of course the delta H can also be written as in the form of the L, this one L minus by this one, yeah, L minus by, and that position is that one, isn't it? That one is L cos theta, L cos. Right? And you can simplify this one becoming, you have L, then you bring out the L. This one is 1 minus cos theta. Okay, but remember, yeah, but theta is approaching to 0. When you are saying theta approaching to 0, when at this point, yeah, so cos 0 equal to what? Cos 0 equal to what? Is theta approaching to 0. Cos 0 equal to 1. So you will have here equal to 0. Is it correct? When you're doing this one in dynamic, is correct. But remember, yeah, this one you have energy. It will keep oscillating over a period of time. And we are assuming that the system will not stop. Huh? The system will be still continuing over and over. So, and it is not correct here. It is not accepted. We cannot accept when the PE becomes 0. So we have to do something about it. So we need to do something about it. Okay. By introducing binomial theorem. By introducing what? Binomial theorem. Or in other what do you call it? Yeah, in other simple mathematics, we call it by introducing Taylor series. Binomial theorem is it's not complex. Yeah, it's a very very widely used in engineering, typically in structural dynamics. I'm going to use the Taylor series, which you already exposed to the Taylor series. So our aim is what? Cos theta will not becoming 0, isn't it? It cannot be 0. So if this is 0, so there is no motion, isn't it? So we are trying to do this one. So in series, in Taylor series, imagine that cos theta is equal to approaching to 1 minus by is a theta square 2 factorial. I think you remember what you learned in mathematics, yeah? So plus theta 4, this one be 4 per factorial. And I also believe that you know what is the factorial. Plus this one theta 6, another one is 6 factorial, on and on here. But our interest is only up to square because this one is not so complex. So we're going to end up with this one. This one, enough to what, to remedy the cos theta. Sorry, it's not the cos theta, it's cos 0. Cos. So you take this one and you put it in the equation. You have what just now? PE is equal to, where P equal to mgl. You have this one just now is 1 minus cos theta. Take this one. Okay, you have 1 minus theta. So that will give you mgl. You will have this one 1 minus 1 plus theta square divided by 2. And finally, you will have mgl theta square divided by 2. So now it is valid for P. So you bring the two energy. The first energy is half. You have I theta dot power of 2 plus the other one is the mg L divided by 2. This one theta equal to 0. This one is basically conservation of energy also, isn't it? When you have 0, meaning that it is in the equilibrium condition. So the energy will be in equilibrium condition. So if you can solve this one, you bring down the power. This one is the constant. R is of course constant. Theta dot, then the other one theta double dot, plus this one, and you have power here. And mg is constant, L is also constant. You have theta dot equal to 0. Then you cancel this one, you cancel this one. So basically what you have is you will have and let put it in let I here is equal to ml square. So if you can solve this one, you'll be getting theta double dot plus this one, yeah. You'll have this one will be mg L divided by ml square. This one will be theta equal to 0. And of course, yeah, the equation also give you, let me put another color here, blue color. So you have this one, theta dot r. That is a two equation. So the solution will be the solution will be theta double dot cannot be 0. And the other solution will simply give you theta double dot plus Tm, and we cancel m, this one can becoming and we cancel L, G by L, theta equal to 0. This is also known as equation of motion. Correct, isn't it? Equation of motion, yeah? And it is not very difficult. So to solve this one, as I already mentioned, to solve the equation of motion, so what you have is you can put it to now harmonic equation. The other one is by equating with simple harmonic motion. Sorry, with differential equation of motion of simple harmonic motion. Is that clear, class? Can you follow me, class? Or I'm doing this one, or perhaps I'm enjoying this one with my own interest. Yeah, okay, thank you, Ko. Yeah. So if you have this one, let's assume that we are going to solve by using the first one. So the first one from harmonics, let theta equal to theta what? Sine omega. You put it at theta naught to differentiate theta and theta, because when you have x, you can put big X, isn't it? You have theta, don't have a big theta, put it theta naught. Okay. This one capital X and X, this one then you differentiate theta dot is equal to this one omega theta naught cos omega t. Last but not least, when you have the double differentiation, giving you acceleration, angular acceleration, which will give you square theta naught, this one sine omega t. Take this one and put in your equation. Zap, put here. Substitute in the equation. So you'll be getting only theta double dot and theta then. So your interest will be, if I can put it here, yeah, so that you can clearly. So now theta, the other one, zap. It should be another color. I hope you can understand the one, yeah. Even though I keep writing so many lines, isn't it? I really hope you can follow, yeah. Okay, the other one is this one is negative omega square. Put it at theta not sine omega t. This one you plus. This one is g by l bracket theta is the theta will be theta not sine omega t equal to 0, isn't it? So you can cofactor the equation, becoming this one be this and this one is a factor, isn't it? So you have plus, put in negative g by l. This one will be your theta naught sine omega t. And you have two solution. Sorry, this one should be omega t is correct, should be 0. So you have two solution where theta naught sine omega t cannot be 0. Yeah. On the other hand, you will have here, you have omega square is equal to g by, sorry, it's not omega square, it's omega only, yeah, it's omega g by. Is that clear? Or perhaps, yeah, or perhaps you can use one by equating the equation of motion with what? Differential equation of motion of simple harmonic motion, where you have remember just now your equation is theta double dot plus what else? G by L. This one is theta equal to 0. This is your equation of motion. And we already learned the equation of differential equation where we have theta double dot plus omega n square theta equal, this one theta, yeah, equal to 0. This one is differential equation of motion of simple harmonic motion. This one equation of motion of pendulum. And as you have this one, you pick up or you select the second term of the equation. Then this one, of course, you can cancel, and finally you have omega n is equal to g by l. This one radian per second, same as before. So in exam, yeah, or in any problem you want to solve, it's up to you whether you are very keen to solve by energy method or you're keen to solve by using what do you call it, classical method. So it's up to you. Unless the equation in exam on the test, specifically mentioning about solve by using which method. Okay, I very much like to say that to student, you have to know everything, but you mastering one methods. Knowing meaning that if this one the equation the equation asks you to solve by energy method, you can solve it. Mastering meaning that You are very much, I mean, you take a couple of minutes to solve the problem correctly. Okay, now let's introduce equivalent method. Equivalent method. So equivalent method, you know, uh, um, is to simplify, isn't it? Is to simplify the complex model. Model means system, yeah. Model means system. System of variation, of course. So it can also be what, or can also what? It can also performing, another model representing representing the actual model, actual model, or you can put the system, yeah. Well, the first one we haven't meet any complex problem at the moment. Now let's focus on the second perhaps second what call it function of the equivalent, yeah. Performing another model representing the actual model. What does this mean? So it simply means that if you have a pendulum here, pendulum aesthetics, then you displace theta dot, theta double dot. This one is theta, small, small acute angle. This one is L, this one also L. This one about O. Plus, any question? Okay, let me ask you first. Any question up to here? Any question? Hello? No, thank you. So this one when at static, then you displace and let it go. Displace, then you let it go. Displace with small theta, yeah. Displace with small theta, then you let it go. But you don't want this. You don't want pendulum. You want to change this one to become some other form of system representing the actual model. Okay, you are saying that okay, I have this one same thing, but instead of putting pendulum here, I'm not going to put the pendulum. I'm going to put spring. This one is K. This one is L. This one is slender rod. Same thing. This one also slender rod. Slender rod simply mean that the mass is so small or the diameter is so thin, so it can be neglected. So whatever now. So from this one to form this one, how is it? How is it? How is it? Any idea how we are going to compare with this one and this one? So we don't want we don't want basically this one, yeah. We want this one. This is what we want. What we want. This is the actual one. This is the new one. What you want is the new one. So from this one, your omega n is earlier g by l, omega n square. This one is omega n square equal to k by m, isn't it? It's k by m. Okay, it's k by m, correct? Because this mass and spring, because pendulum, the actual one is pendulum, this one is spring mass system. So if you equate these two equations, you equate this equation, you will get g by l is equal to k by m. And this is not k, put it the kp, k for pendulum, k for pendulum. Okay, k for pendulum. So what happen now? So you basically put it the kp is equal to your mg by l. So it simply means that if you want to change from one form of system pendulum to become another form of system pendulum, you need to know what kp is. So your Kp now is equal to mg by L. What is the m? Is the m for pendulum. What is the g? Of course, gravitational force. Yeah, and this is your L. This is your L. This is your. You maintain the length of the slender rod. That is one of the component or perhaps the objective of having equivalent system. Okay, any problem before we move to the actual equivalent system? Any problem? You know. Okay, now before we move to the equivalent system, I'm going to look it at the third system where you have shaft plus rotor, or some call this. This one is typically what for torsional vibration. We are going to look for overview. It's not the whole thing. It's only an overview of the system. The reason is why. The reason is the torsional vibration is it's not very difficult. But you need more time to basically study the torsional vibration. And as I mentioned couple time, if you want to if you want to know better about the vibration, you have to do the option core subject in the mechanical vibration. Okay, this one, yeah, shaft and rotor. For example, here a very simple system. Say that you have a shaft, uniform shaft fixed at one point, and you have rotor. From one view here, your rotor is this one. So you have two conditions. You have two conditions. One condition telling you that you will have a linear motion. The other one is telling you that you have the torsional vibration. The torsional vibration will not be part of your solution as I mentioned earlier, but the linear the angular motion will be part of your solution. So let's assume that we're going to put on this simple one. So this one, you push, you displace. This one you give moment. Two different things. This one will be twisting. This one display mean will be deflected. Correct? So this one, when you twist this one, this is the what? Yeah, when you twist this one, you will creating torsional. And torsional will not part of your syllabus. So this one is exactly as when you displace the thing, and the only thing they will be deflected. So it will be deflected a bit here with theta. Theta dot theta double dot. Okay, and you found that this one, yeah, and you found that it will be what? It will be exactly as what you did in this one can be we can be represented by spring and mass system. So you have to create perhaps you have to create free body diagram, and this one will displace a bit, and as you displace this one you have K here. K here is put it KT. T is a torsional. So you have KT will not allow you to go. This one will be delta plus X. The other part will be you have this one mg. And if you look at this one very careful, it's very clear that similar mass to spring mass system. So I'm in conclusion, I'm not going to do this one. Yeah. The only difference now you have this one is KT. This one you have a KT here. KT is the stiffness of torsional condition. The spring is K. This one is KT. T for torsional. So this one you can read book and look at your book. Turn to page 247 for detailed information. Okay. Any question? plus. Okay, now I'm going to do the equivalent method now. Before we move to the actual thing, we are going to look for equivalent EQUI method. In equivalent method, you have three different parameter. One will be your M, K, and C. This one is not studied yet. This one, the damper, will be in the next coming lecture, because this one is basically talking about damper, and we are talking about no damper system. So this one is mass, this one is K. So if you have M here, you can, you can change from M to become M equivalent, or you can also put the M prime here. From K here, same thing, you have K equivalent and you put it M. Of course, K and K cannot be K equal to M, yeah. This one K is K prime. Same thing here, you have C equivalent equal to C prime. All the prime or EQ is equivalent to the actual system. This one all actual, this one actual, this one new. Okay. Any question? No. No. Okay. Still okay. Okay, now let's assume that we have a system where number one, you have slender rod, then you have mass, then you spring here about O, A, and B. Okay, from this system you have two choices. Okay, you have two choices. One will be you move M, this M, yeah, on top of K. This is K, K. Or perhaps I have to say that on top of K, because it will be on top of K here. So it simply means that if I can put another color here, yeah. So this one you put M here, zap, it becoming, it's not M but M equivalent or M prime. Okay, or in other word, oh sorry, in other solution, you might be thinking not to move M but to move K. Now you move K, you know, you move K and put underneath or under M. It basically underneath M, yeah, under M. Hopefully you understand. So it is not K now, becoming K equivalent or K prime. It is, as you move, it is not M now, becoming M equivalent or M prime. So it simply means that you have this one. Very difficult to draw the dotted line representing the spring. So I'm going to put here in different color. Yeah, hopefully you can differentiate. This one is now it is not K but become K equivalent or perhaps K. Who decide? The problem now. Who decide? Who decide? Who decide? You are going to decide. But of course, before deciding one, before you decide one, whether you want to move K onto K, you have to know how the transferring. Move mean you have transfer. Yeah, move mean that you transfer. Move mean that you are transferring K. Okay, let's now number one. Did number one again? Never mind. Yeah, I lost my numbering. Sorry about that. So now let transfer M. M become M what now? Become M equivalent, or I put it as M prime. So same now, same what? Same what do you call it? Same system. This one is the actual one. This is the actual one just now. This is your spring about O A plus B. This one is your M. This one is K. So before that, why? Before that, why? Why we do this one? Anyone? If you don't want to answer this one, so I don't want to give you why, or what is the reason? What is the reason of EASON of transferring M or K? If you can help me, I'm going to give you the answer. Otherwise, I will keep like that, and you have to check on the answer on your own. So, what is the reason? Could anyone tell me? You can speak up, or you can also write something. If you write something, sometimes I can't catch up. That's good because the pop out, pop out what thing that you want is very fast. Anyone? So if you don't want to respond, mean that you are not interested to know why. What is the reason? Okay, now I'm going to
Easy the
I'm going
calculation.
to sorry.
Easy the calculation for the fluid body diagram. Maybe.
No, good try anyway. What is the reason now? What is the reason of transferring this M and K? Okay, now let me explain, or let me ask you. Who's on the line? Tan, is it? Who's on the line just now?
Yes. Yes, sir.
Tan. Okay,
Ah,
this is what. This one is spring MS system or what? Spring MS system, isn't it?
yes.
Yeah, so for spring MS system, your omega n is equal to K by M. Am I correct, not?
Yes, sir.
Correct. So you have to maintain this equation. As you have maintained the equation, it simply means that it's no longer K, becoming K equivalent or M equivalent. So that is the reason. Okay. So if you want to transfer M now, your equation now, what is your equation just now? Is still K by M, still K by M, still K by M omega K by M. This is your equation. But now it is no longer M because you're going to transfer M, so it becoming K will remain as it is, but M will become M equivalent square root. Understand me or not? So the one that you keep transferring or move, yeah, it become equivalent and equivalent. If you're saying that you're going to transfer K, for example, yeah, so your K is no longer K, becoming K equivalent. Is that understand? Is that clear? So later on you have C, for example. If you transfer C, becomes C equivalent. Okay, so now, so the system now becoming, you have transfer M just now, isn't it? So becoming here, and your M will be here, but remember this is not your M, but M equivalent. Because you already transfer or perhaps M prime. And the spring will be maintained as its own position where you have K now. And the distance about O now is becoming A only. So how are you going to look for omega n? You need to give displacement. So I'm going to give displacement here. It will displace by omega. Sorry, omega is not omega. Yeah, theta, theta dot, and theta double dot. The same condition I'm giving here. Same thing, this one also theta, theta dot, theta double dot. So then we check energy. Remember when I talk about equivalent method, energy will be always be the same. So energy must be the same. Must be the same, yeah. So now, what energy will involve when you have what they call it, when you transfer M, it give you kinetic energy, isn't it? So you have put it here as you put it E energy, yeah, or put it a delta E, or you can also put delta T. Doesn't matter what sign you're going to put your delta T, for example. If you're C2, you learn in your dynamic, you put the delta VE, for example, VG, isn't it? For for this, what you call it, the VG for gravitational, put it here V. What do you have for delta V? What do you have for this M? The put it E only E lah, energy. E initial is equal to delta V also. This one delta for the new. or put it here, equivalent. Huh? So the energy that we calculated earlier, if you remember the thing that you calculated so many times in our course here, you have the half m v square. You don't have v here, is it? You don't have v here. You have to convert this one to become half m x dot. Okay, it become x dot, or it become whatever dot z dot, doesn't matter. So assuming at initial this is the position, it will move here. This one put it in x. This one will move small portion, put it in y. Okay, so you have the equation. This one is half the actual m x dot power of 2 is equal to half. This is not m but m equivalent y dot power of 2. Correct? You will start with x, then you, this one x meaning that you displace, then what? Then you let it go, so it becoming x dot, it becoming x double dot. As the velocity keep changes, the same thing happen here. Y then become y dot and become y double dot. You have x dot, but remember, yeah, remember about segment equation. What is segment equation to you? Remember the segment equation you learned in many years in your study. We have S is equal to R theta. Correct or not? Yes or no? Yes or no? So this is segment equation. So if you found this one, if you look at it, it's very similar from what you have learned in segment equation. It's simply now, it is not x but become, sorry, it's not s become x equal to r will be r theta. So in here, for example, if I can put it here in equation, I'm going to put another color so that you can easily differentiate. So this one here, for example, x will be what? Equal to a plus b theta. X dot equal to a plus b theta double dot. X double dot will be a plus b theta double dot, where you found that your a and b is a constant parameter. Same y double dot equal to a theta double dot. You understand me or not? Is that clear, class? So if you clear this one, I can proceed the next step. Then we will conclude with the general equation. Because I don't want you to memorize everything. I want you to, I basically want you to derive your own. If you suddenly forget the equation, then if you have this one, then you can simplify half. This one is m x double, put it here. So you have a plus b square theta dot square is equal to another half here. This one is m equivalent. Your y double dot will be here is a square theta square. You cancel half, you cancel half, you cancel theta dot, you cancel theta dot. And finally, your m equivalent, because this is your aim to define m equivalent, is basically your m, isn't it? This one is a plus b divided by a power of 2. So your new equation now, your new equation omega n now, from the general equation k by m, it is no longer to be that equation. It becoming k will maintain as k. Your m now is becoming m equivalent. It becoming m, this one a plus b divided by a power of 2 square roots. So this is your natural frequency. When you move m, okay? Okay, class? Okay, yeah. Now I'm going to move. Let transfer m. Sorry, let transfer k. Number 2 now. Let. Remember, when you transfer k, k will not become k, or k becoming equivalent. Or in my notes, yeah, I put k prime. Let transfer k. So the system that we have earlier was here. This one, same system, of course, yeah. This one, you have a mass pointing. Sorry, pick this one end at O. At the middle, a spring. This one A and B about O. This one is M. This is your K. So the system now, as you decided to transfer K now instead of transfer M, who decided just now? You have to decide this one, isn't it? So it becoming ZAP, M will remain as M. The distance about O is A plus B now. So your K will be here, and it is no longer K, what becoming K equivalent. Of course, yeah, in exam or test, you don't have to describe this one. You are going to draw everything. You have to understand how do you transfer. I will explain how do you use the equation later on. Yeah. So now remember, you will not have omega n unless you give a displacement, isn't it? So you displace this one. This will give you theta, theta dot, theta double dot. Then you displace this one with the same parameter, theta, theta dot, and theta double dot. And this is your K just now. This one is the small portion. Put it the K here, X. Put it here now, Y. And your energy, put it here, delta E. This one is initial. Sometime in my note, I put it before and after. Sometime initial and new. Basically the same. Delta VE. This one is new or equivalent. Or before, sometime after. So this one, you know that when you are talking about spring, energy involved is, what is the energy involved in spring? Is a potential elastic energy, which give you PE is equal to what? Half K X, half K X square. So you put it here. The initial one will give you exactly as the general equation here. And when you have a new one, which is now, it's not Y, sorry, it's not X, become Y. So put it here. Half is half, but it's not K, become K equivalent. Now it's Y square. And same thing, applying the segment equation just now, you will have X equal to A theta. You have Y here is equal to A plus B theta. Put in the equation, okay, X will be A theta, A square theta square plus, it's not plus, yeah, equal half, this one is K equivalent, Y will become, Y is A plus B, isn't it? So you have A plus B square, then you have theta square. Again, cancel this one, cancel this one, cancel this one, and this one. You are going to perform the A equivalent, where your A equivalent is basically the actual K, multiply the actual length divided by the new length B. And your omega n now becoming, K by M. It is not K by K equivalent, it becoming K. This one A plus B divided by 2. This one be your M. An equation. So please do not memorize this one, because so many minutes you have to memorize. What you have to do now is basically what? To understand how to go about it, rather than keep memorizing every equation. Just remember that whatever you have, whatever you do is to ensure that this one, energy before, put it there, before is equal to energy after. When you move, it become a new one after. This one is in consideration of energy. The reason is why, you keep memorizing. If let's say that I'm going to give you something else, for example, perhaps I'm giving you the crank lever. This one you have mass. This one you have spring. So mass you have spring. So this one, put it the M1, put it the M2. This one you have K. So this one now a bit complex, isn't it? So this is what you think about O. You want to check one, you want to define the omega n. Of course, the omega n is always given by the equation that K by M. The general equation is K by M. Doesn't matter how does it look like, yeah? It's basically K by M. But remember this equation, this equation only mean for For what? For this one, this type of system. Remember that K and M. Where you have K and M is one plane. This one plane system. This one is so many planes, plane, isn't it? System. And it called so-called as a complex system. Because why? Yeah, because K and M is not located in one plane. K this side, M the other side. You can also put K here if you want to, so. Huh? So now, let's say if you have this one. So let's make it a bit simple now to ensure that you really understand this one. Bit simple where you have, yeah, only mass. This one is A, this one is B. Only mass. So you have two what do you call it? Two choices. One will be you can move to this one or you can move to this one. So perhaps you move to that one, to the mass here. You can move at number one, you can move at two, or you move, meaning that you transfer the mass. Yeah. So now let move at two. So you have how many mass? You have two masses. No spring, isn't it? What is the distance? Is A. It's not spring here. If you have spring here, for example, if you have spring here, for example, you have spring here, for example, a spring is K. Of course, you need to move K here, isn't it? You move K to here, it becoming. But remember, it is no longer K, becoming K equivalent. So what is the M now? M, this one is M1. If this is what M2, for example, so this one be M1, this one become M2. This is what we call, we lump the mass. Okay, I'll be explaining this one further when we meet all type of equation later on. Yeah, but now at the moment, let us now make a simple thing. So now, how is it? Can anyone tell me how I'm going to change this one, omega n? So omega n is equal to what? K by M. You have K, but it's not K, but K equivalent. You have M, but not M equivalent. You now do one after another. Put it M equivalent. So your M equivalent equal to what? Your M equivalent equal to the M2. Put it there, M2. Isn't it? Because M2 here is at, no, M2 not move. Plus, we have another one, M1, but equivalent. This one you move. Of course, yeah, this one is for lever. Crank lever, it's not lever, yeah, crank lever. So for the crank lever is typically given by I equal to mk square. This one is very typical in this in this crank lever. Given this one, what is kk is a usual is crank, is a radius of gyration. So you have the M2. This one is equal to, you can put it the M equivalent, isn't it? M equivalent plus this one will be your I. Astaghfirullah, it's not equal, yeah. I say plus but put it equal. I say equal but put it plus. Equal to I about O. This one also O divided by K square. K square is equal to A now, is equal to I about A square. So put it here, plus, now it's plus, yeah, plus, you have I about O divided by A square. That is your M equivalent. Okay. So what about your K now? K equivalent. So could anyone tell me what will be your K equivalent now? Just now you have the equations just now, right now. Let me explain to you. Look at now, focus on K now. K is here. about what just now? About A. We move this one to become here. This one is K. This one is not K, but K equivalent. Okay, look at your class. Look at your class. Focus this one. You have earlier just now, this one, remember this equation? I'm going to use this equation. I'm going to use the equation and I'm going to simplify the equation so that you can easily understand. Okay, now, look at here. You have K multiplied by A, the actual one, the actual length about O, equal to the new K multiplied by the new length about O B. Do you understand me or not? Is that clear? Hello? Yeah, remember, yeah, this one all new. Oh, sorry, this one all initial. This one all new. So you simplify because you came to define what K equivalent. So your K equivalent is equal to your actual K. This one is A plus B equals square. So please do not memorize. What you need is to understand how to go about it. This is the principle. The principle. So now your omega n is equal to K equivalent divided by M equivalent just now. It's basically K A plus B power of 2 divided by M2. This one is M2 plus I O A square. Of course, the unit will be radian per second. Okay, so that is one. The other one, yeah, if you have a solid disk, for example, with R, this one with M, rotating about O, rotating about O. This one is M, yeah. So now change solid disk to become lump mass. Change solid disk to become lump mass. How is it? You have, okay, first is what? First is maintain this one, yeah. First is maintain R as constant parameter. Maintain R as constant parameter. How is it? You maintain R about O constant parameter. Then you have a lump mass. This one is lump mass. Lump mass. It is not M but become M equivalent. This one is the big M. So if you look at very careful here, your I here is equal to half mr square. Your I here is equal to what? M equivalent r square. So you maintain radius M parameter as a constant parameter. So finally you have I. This is I initial is equal to I equivalent. I equivalent or I new, put it the I equivalent, or you can put it as I new. So finally what you have is I initial is half mr square equal to, remember this is M equivalent, and you maintain the R will become also square. And of course, yeah, this one is coming from the equation R equal to M K square, where your K will be the radius of gyration. And if you if you want to define what will be the M equivalent look like, so your M equivalent is becoming, so you will have, okay, M equivalent to half. This one is M, R and R cancels. So this is your new mass. Do you understand me now? Yes or no? Yes or no? Anyone? Okay, last is let us now talking about spring configuration. Spring configuration. or in other words, yeah, it's a spring arrangement. So in spring arrangement, there are two type of spring arrangement. One will be in series, S-E-R-I-E-S. The other one is in parallel, P-A-R-A-L-E-L, parallel. And this one is very much like what you learn in uh, electric technology, where you have the capacitor R and also the current, isn't it? So your capacitor is, or your resistance is always resistant to the current. This one, the spring is also, is also resistant to the motion. So a spring in series, for example, put it the simple one first. Spring in parallel. Spring in parallel, for example, you have this one in your note. You can turn to page 253. Spring and parallel, typically when you have a spring in parallel, one spring, two spring, three spring suspended by M, and this one will be, this one K1, this one K2, this one K3. And when you displace M, you displace this one, displace with X dot, X double dot. First you displace with X, displace and let it go. You displace, you become displacement, then you become velocity, and the velocity keep change as the displacement we can keep changing, you become this velocity, and the velocity keep changing from higher to the lower, or vice versa. You find it becoming an acceleration, isn't it? So you found that when you displace with X, for example, you have K x1 is equal to x2 is equal to x3 is equal to X equivalent. This one is very logic, isn't it? When you put down here, this one all K will be also displaced with x1, x2, and x3. You found that the all X is the same as is attached to a single mass. And finally, that if you can put this one in equation, for example, put it in equation. Also, what you have in equation is half. Remember, K equivalent. We have another one is X equivalent square is equal to half K1 x1 power of 2 plus half K2 x2 power of 2 plus half K3 x3 power of 3. Then this one all cancel the square because it's a cofactor to everyone. So you know that this x1 equal to x2 equal to x3, isn't it? Because you know that this one. So basically, we have K equivalent is equal to K1 plus K2 plus K. Or I put in my note that K equivalent is basically the summation of all K by N, where your N is start by 1, 2, 3, 4, so on and so forth. So that is one. And last but not least, talking about theory, we have not reached our time yet. So this one talking about theory for in series, for example. So the series here, you know that when spring attached by series here, you have, okay, we have one spring here, then connected to another spring, then connected to another spring, put it a K1, K2, and K3. Obviously, this one you will have the X1, this one you have the X2, this one of course you have X3, and then you put F, otherwise it will not move, isn't it? Put F, or you pull, you displace and let it go. Don't put F, because as you put F is always there. So you put the displace and let it go, let it go. Right? So you'll be using the same equation, but this time around, but remember, x1 is not equal to x2, is not equal to x3. Okay. And when you check the equation, finally you have the I K equivalent is equal to I plus it's not I, sorry, 1 by K equivalent by 1 is K1 plus 1 by K2 plus 1 by k. A very similar with the equation that, you know, if you remember, I by R total resistance is equal to I by R1 plus I by 1 plus R2. This is not I, 1. Remember, this one is the this one is for the resistance, whereas this one is spring. In principle, of course, spring will be resist the motion, resistance will resist the current. So I think that is all the theory about undamped vibration. The reason you need to know about this arrangement of spring because what? Because this one, because you need to know the reason, because as you have, for example, you have this one. Let's see, you have a spring. So you have mass. You have mass here. You have a mass. You have spring here. Yep. Astaghfirullahaladzim. You have spring here. So this one will be basically you have mass, spring here. If I can put it at K1, this one is K2. You have this one K1. This one also you have K2, and it look like a parallel arrangement. A parallel arrangement, isn't it? But when come to a mass, a spring first, a spring attached to a mass, then a spring back, another spring. You have K1, K2, this one K3. This one is become a problem to you now. The reason is why, because you have the combination of parallel and series. So you need to solve this one. Solve K2 and K1 in series. Get K equivalent. This one, then solve K3 in parallel. So to simplify the equation, it's become M. This one is K3. This one you have a single spring, but this is K equivalent. But this, remember this K equivalent? This K equivalent is what just now? It's equal to 1 of, it's not correct, yeah? 1 upon K equivalent. 1 upon K equivalent is equal to 1 plus K. Am I correct or not? Plus K1 plus 1 plus K2. Put here. Okay, now tell me, how do you solve this one? Yep. End up with, okay. Tell me, how do you solve this one? Let me here, yeah. How to solve this one? How? Anyone? Anyone? How to solve this one? Anyone? Anyone? Hello? Anyone, class? How to solve this one? Yes, done.
K1 times K2 divided by K1 plus K2.
K1 plus
K1 times K2 divided by K1 plus K2.
correct. Correct, yeah. And what type of mathematics this one called, or what type of mathematics this one called? Arithmetic called formula or theorem is what? It's a cross. It's a cross what? It's a cross multiplication, isn't it? So this one you learn this one, yeah. Okay, so I'm going to share with you this one. We completed this one. Alhamdulillah. I'm going to share with this one. Okay, we completed this one already complete. This one, yeah, this one. Even though we haven't touched this one yet, because I don't want to go back to the theory. So let me have you know, couple of minutes to solve this one. I'm going to share this one with, yeah, here, yeah. Okay, now look at here. So this one is a damping. Even though we do not know what damping is, just just pretend yourself you know what C is at the moment. Just know what C. It's not damping yet. C just now, huh? But the theory is going to be the same. Just pretend that you know what C is at the moment, huh? So now I'm going to share with you how to solve it. So this is the C. This is the C. Now you have two choices: to put C here underneath M to become C prime. If I can draw this one, very quick one before we end our session today. This one is, sometimes you have C and K, sometimes you have C alone. This one, C is damper, yeah. This one is M. This one is O. This one you have C. That is the model C, the dashboard. So C is A, B. So you have to move C now, move C under NEA needs underneath or put it there, or I put it there just under M, under M, put under M. Needs is NEATH, but put it under M, put it under M. So your system now becoming ZAM, Messier, about O is A plus B. Now you have damper, but the damper now is not C, but becomes C equivalent or C prime. So your delta V damper is initial is equal to delta V damper, but a new one. So the delta V damper is given by, let assume again, let pretend that you know what C is, isn't it? So let C, energy of C is half C x dot square. This one, yeah, this one, the energy of damper is this one. So the initial part, of course, when you displace it a bit, when let now displace a bit, zap, displace this one with theta and theta dot and theta double dot. You have this one, the displacement of the original, this one, the displacement of the new, theta dot, theta double dot. This one is a new, put it the SX, put it the SY. So your X will be A theta, your X dot will be A theta dot. And of course, your X double dot becoming A theta double dot. And a new one, Y equal to A plus B theta. We have Y dot is equal to A plus B theta dot. Y double dot is equal to A plus B theta double dot. Okay. Then we put initial now. So the equation is this one. Half C x dot square is equal to half C equivalent Y dot square. Then you substitute the known parameter as you given from the equation, segment equation. Put it half, C will remain as C, x dot will becoming C is A square, theta dot square is equal to half C equivalent. This one is Y dot is A plus B square theta dot square. Same thing, isn't it? So you cancel this one, you cancel this one. Of course, theta dot cancel, theta dot cancel. So you have C equivalent is equal to the actual C. This one is A plus B. A divided by A plus B. A divided by A plus B, the whole thing square. So now is your new, C. So if you look at this one very carefully, you found that this is exactly the same from the spring. Say similar to K equation. K equivalent equation. Okay, one more thing, one more theorem. So beside using energy to find the to find the equivalent EQUR equivalent parameter, we can also use I. Typically for M. Okay, so for example, this one. For example, just now you have this one M, yeah, this one M. This one is A, B. This one is A. So your system is becoming here mass about O. This one is A. Now is spring. This is K, still maintain K, but it's not M equivalent. My task is to define what is the M equivalent. Do you understand me? The last one, this one, class. Do you understand this one? Yes or no? Yes or no? This one is very quick compared to energy. This one easy and quick compared to energy. Do you understand what I'm going to do this one, class? Okay, just now we use energy, right? What type of energy? Kinematics. Kinetic energy. I'm not going to use energy now. I'm going to use mass moment of inertia, which is very, very simple compared to the energy. So now put it here. Put it here before that, so that you understand. Delta V E, this is T, this one is initial, equal to delta VE, this one is a new, done. We already done this one. And now we use alternative methods. More simple and easy. How is it? I initial is equal to I equivalent or new. I initial, look at here, I initial. Mass moment initial about O. It's not also about O. So look at here very careful. If you want to use this one, look at here very careful. So this is M. So this is O. So you rotate about A and B. So you have I is equal to M. This one is A plus B power of 2. This equation is coming from I about O equal to M K square, where your K equal to A plus B. Okay, it's equal to now M equivalent. Look at M equivalent here. Only A. This one will be A power of 2. This is the same thing. Your I now about O, but now M equivalent about A square. It's coming from the equation of M equivalent K square. Correct? Easy, right? So now you have the M equivalent is equal to, we have the actual M, this one A plus B divided by A. Is much, much easier compared to energy. Okay. Any questions? So I think we concluded that I already I already discussed the whole thing about undamped vibration, free undamped vibration, the energy method, and also the equivalent method. The last one is one. So when I meet you again, inshallah, tomorrow morning at 10, I'm going to give you example how to use equation. So defining equation is one thing, not is solving and using equation another thing. So now next meeting is about how to use all equation. Okay, class, any question before we end our session? We're now reaching our time, 9:45. I don't want to hold you. In my class, you have perhaps you have another class. I don't know. Any question? No, thank you. Nazifa, thank you, Ko Lee and Lee and also Ko. So we really hope you enjoy my lecture. So when I see you again, inshallah, we're going to look at another example, to use the three method. Yeah, we're going to use the three method to solve a problem. So then you decided which method you really want to use in the exam or in the test. So you have to know every method, but you have to mastering one of the method. Mastering one of the method is easy for you to solve in exam. And I will, frankly say that in the exam or in test, there will be no specifically mentioning about using a method. You're going to have an open equation, so it's up to you to decide which method you feel that very convenient to use it and solve it correctly, of course. Yeah? So with that, I end my session, I end my lecture with Assalamualaikum warahmatullahi wabarakatuh. Thank you for attending my class. Wish you all the best and wish you stay healthy and stay safe. So with that, I end and I see you inshallah. Have a nice day. Thank you, viewers.